All right, welcome everybody. So whether you are architecting a new application that has multi-region requirements, or if you have an existing application that has new requirements that mean you need to evolve it into a multi-region workload, there's a lot of considerations and a lot of things to take into account here. So I'd like to welcome you to this year's edition of Best Practices for Creating Multi-Region Architectures on AWS. We've ran sessions with a similar title at past training events, but every year we like to take a different lens and a different viewpoint onto this important topic, simply because there's just only so much that we can cover in the short amount of time that we have. My name is Joe Chapman. I'm a Principal Solutions Architect at AWS. I'm joined by my colleague Sangjun Kim, who is a Technical Account Manager, as well as Jaemin Kim, who is the DevOps Lead at Samsung Electronics. So the specific lens that we're going to be diving into today is all focused around or centered around failover and how you can think about multi-region architectures with failover in mind. So we are going to start, as many should, with the fundamentals. We're going to dive into the 4 published AWS multi-region fundamentals, and then we're going to keep that specific lens on failover best practices with those. Now, applications can be large and complex, and it seems like every day they're evolving faster and faster. So next, we're going to look at different organizational failover strategies to help you understand and figure out what to actually fail over when some kind of an impairment happens and you need to go through the failover procedures. Then a question that I get asked a lot in a bunch of workshops that I've run in the past answers a very tough question that doesn't have one simple answer, and that is, how do I know when to fail over my workload? So we'll talk through some best practices and considerations that you can take and apply to your workload to really answer that question as to when do I fail over this workload. And then I'll hand it over to Jaemin, who's going to talk through the Samsung story as to how they evolved from a single workload in a single region to a multi-region workload. He'll also talk through different failover strategies, how they think about failover, and how they actually go forward executing on that. So when building on AWS, customers benefit from 34 available regions that are available all around the globe. We've already announced the availability of 5 more that are going to become available for customers in the coming years here. This provides choice and flexibility for customers to deploy their workload where it matters most for them, maybe closer to their end users or closer to what is going to serve their application the best. And it's important to note that every AWS region is built to be highly resilient. For example, every region has 3 or more availability zones to give you multiple availability zones to architect your application, not just within a single data center. We also have architected our regions so every region is able to operate it is built to be fully independent of the other regions. With that, so even though every region is built to be fully independent of the other regions, they are connected through high throughput, low latency, redundant fiber optic networks. We call this the AWS Backbone Network. This AWS Backbone Network offers a consistent experience for end users. Once you're on that backbone network, you can expect low traffic, low packet loss, low latency, and overall high quality network experience. And to bring workloads even closer to end customers and to your users, we have over 600 points of presence where you can utilize that for things like caching and getting your customers onto the AWS Backbone Network quicker. We also have over 41 local zones today, as well as 29 5G wavelength zones. And what these zones do is it allows you to build your workload and put compute even closer to your end customers and to your end users. It's easy to say just by looking at this, right? The AWS global infrastructure is large and expansive. It's built to be highly resilient and is continuing to expand. This allows customers to build applications with the most stringent requirements, whether that is for scalability or performance or resilience. The AWS global infrastructure allows for that. As I'm talking with customers, and I've had a lot of conversations, especially over the past 5 or so years, helping customers to evolve into a multi-region workload. And as I'm having these conversations, I'm finding that customers generally fall into one of 3 groups as to why they want to go down this route. The first is for improved performance. So here you may have a requirement to offer a consistently low latent experience, a high performance experience for end users that are geographically dispersed. Sometimes this may mean that you need to deploy to a multi-region active-active type of a setup, but not always, right? Because we have that AWS global infrastructure that we just talked about, and there's a lot of things that you can take advantage of by simply getting your customers onto that AWS backbone network, utilizing points of presence, and speeding up the overall delivery of the application. The next reason is motivation is for regulatory requirements. So as you expand your application, global expansion means that you may be serving users in different geographies in different countries. These different geographies, these different countries may have different laws that dictate what data can live where and how it can move. So I find this most commonly in areas of high regulation, such as financial services or healthcare, or also just with any user-sensitive information. What typically ends up happening in these regulatory requirements is that customers end up deploying multiple iterations of their workload into different regions. In these, each deployment is going to be completely independent of every other deployment, and then usually a strict share nothing policy is going to be enforced to ensure that data doesn't accidentally leak outside of that geographic boundary by replication or any other accidental movement of the data. The final reason then is for increased availability. And this is providing customers in your workload the opportunity to recover your workload in a completely different location, maybe like a different AWS region, in the event of some kind of a larger impairment. And this is where we are going to be spending the most amount of our time today as we look at some of the characteristics for failing over with a multi-region architecture. But what we're trying to do here is just overall improve the availability, whether that is by reducing any type of outage within a single location, or making sure that we can fail over quickly and efficiently. Next, let's take a look at the AWS multi-region fundamentals. We won't have time to go into depth within each of the 4 fundamentals that we're going to talk through today, but there's a QR code on the screen here where you can find a lot more information. There's a full white paper there that goes into a lot more detail on things other than just failover. But as we are limited on time, we're only going to focus on the 4 fundamentals with that specific lens of failover here. And the first fundamental is to understand the requirements. So by defining and bounding your recovery time, you're able to set appropriate expectations for how long the recovery process is going to take in the best case scenario and in the worst case scenario. And so what this allows you to do is a few very, very important things that you can build off of. Number one is you're setting appropriate expectations for stakeholders, for customers, as to if there is some kind of an impairment, how long that impairment is going to last, because we have a bounded recovery time. You're also able to take a look on the technology side to make sure that working backwards from that bounded recovery time, that you have the appropriate architecture set. You've set the appropriate design decisions such that from a technology standpoint, you can recover within that specific period of time. And working backwards from that defined goal is a very, very beneficial item to do. Now, measuring and tracking recovery times means you need accurate tracking at every step within the process. Many times as I start in some of these engagements, we start to think about, our recovery time is just from when the failover is initiated until the failover is actually fully complete. But in reality, the recovery time is from when the problem first starts until when the recovery is fully complete and the impairment is fully resolved. So, if we're looking at the full extent of our recovery time, our problem first starts after some time, hopefully not too long, and hopefully by our own observability tools, there's going to be a detection that is going to happen. That detection should very quickly send a notification to somebody. Maybe that's an on-call engineer, or maybe that's a network operations center, or somebody else to take action on this actual notification that was detected. Then, after maybe some troubleshooting, after going through some runbooks, that individual is unable to resolve the issue, then there's probably going to be an escalation that happens. That escalation could be to a higher level engineer, or it could just be to somebody that is a decision maker that can make the decision as to what needs to happen next. All of this is keeping in mind that bounded recovery time. So that decision maker or that next level engineer may make a declaration saying, hey, okay, we've already spent X number of minutes on this problem. We need to execute our failover, or we need to take the appropriate next steps. If we do, then there's going to be a declaration that's going to be made. That declaration is, hey, we need to declare a failover, and at that point, the failover is initiated and the failover is complete. So as you're looking through this, make sure that you're looking at all 6 of these steps and try to find efficiencies and areas of improvement to overall improve the recovery time by reducing the time spent at any one of these 6 steps. And by setting and accurately measuring objectives, you can bring more expectations, and you can set better expectations for that bounded recovery time. A common way that customers measure availability is with the 3 terms on the screen here. The first is MTTD, so mean time to detection, and this is measuring the time from when the problem or the issue first started until something detected it. Hopefully our own observability stack has detected it. And then we have our MTTR, or mean time to recovery. And this is measuring the time from, again, when the problem first started until the actual repair was fully mitigated. And then finally, we have our MTBF, or mean time between failures, which is essentially measuring the time from when the last failure was fully mitigated until the time the next problem happens. So really, the time that our application is fully healthy. And by taking a lens at all of these, we can, for example, improve our MTTD, our mean time to detection, by improving our observability stack, adding new monitors, making it more efficient. Then we can reduce our mean time to recovery by implementing automation within our recovery path, maybe with automated healing of EC2 instances or setting up multi-AZ RDS databases that will automatically do the failover for you. And the end result there is less failures, less frequently, and overall higher availability for your workload. Fundamental number 2 then is to understand the data. So data is complex, and dealing with data across distributed locations, especially the farther away the data gets, the more complex it gets. And this added complexity needs to be taken into account. And to meet your bounded recovery time requirements, you need to have a really good understanding of the data. For example, where does the data live? Which seems like an easy question, but when you really dive into it, it's not as easy as you might hope. Where the data lives, where the data lives, how is the data replicated? Is it replicated in real time? Is it synchronous? Is it asynchronous? What is the consistency level of the data, whether that is strongly consistent or eventually consistent or something in between? And then finally, what is an acceptable amount of data loss in the event of some kind of a larger impairment? And all of this needs to be tied into your recovery objective. So for example, if your recovery point objective is such that you need to your recovery point objective is such that the replication delay needs to be under a certain threshold, you need to fully monitor that. And then if your replication delay is longer than the recovery point objective, there's something that needs to be seriously looked at for the architecture. Likewise, the time to recover the actual workload with the recovery mechanisms and that whole recovery time should all be tracked as we're tracking that full recovery time. For example, if you're not able to meet your recovery times because you are executing on a backup and restore policy where you're restoring backups and that restore is taking too long, maybe you need to think about changing to a strategy of active replication, just so you can fail quicker and that recovery time can be reduced to meet your requirements. Fundamental number 3 is to understand dependencies. So to ensure the operation of the workload during a failover scenario, you should have no dependencies between the 2 regions or any of the other regions that you have. Region 1, in this example, should be able to operate 100% fully independent of region 2. And what this allows you to do is set that defined fault isolation boundary, such that if something happens in region 1 to the workload there, that issue is going to be bounded to that fault isolation boundary. Likewise, when we're thinking about how we are actually going to recover the workload, all recovery actions should be taken from the recovery region. We don't want, within our recovery processes and procedures, to take any dependencies on a potentially impaired workload. And then finally, as you're mapping out dependencies, which I know is tough, especially as we get into microservices and very complex interactions between microservices and that complexity there, one way that I found that is really beneficial, that works well, is to map out your critical user stories. So a critical user story, for example, for an e-commerce platform, might be a user going to the site, browsing the item catalog, adding and removing items from the shopping cart, and then finally completing the checkout process. For me, for my e-commerce application, that is most important. Now let's look at the dependencies at each step within this user story so we can understand what the hard dependencies are, what the soft dependencies are. And then we can further map that out. So we have our most critical user story to the other user stories that are going to be very important, but we can actually prioritize the dependencies and we can prioritize how we're going to change the architecture to meet our recovery requirements. And the last fundamental all comes down to operational readiness and continually improving your operations through your multi-region application. A lot of this comes from your clearly defined goals that started within understanding the fundamentals, our fundamental number one. This is about actually executing on it. So the best way to improve a failover process is to actually test it in a controlled fashion. When you test that failover process, you're going to learn a ton about it, such as different scaling characteristics, different dependencies that you were maybe unknown, maybe service limits that you didn't know, or maybe there's some configuration drift from one region to the other. Also, as you're going through the operations and your policies and procedures, you'll find areas of improvement for improving your runbooks or reducing overly complex pieces of that step-by-step guide that you have. And then the final piece here is on that observability component. So everything that you're going to do, you want to continually figure out how to have a full 360-degree view of the overall health of your application. One way to do that is with a thing we call differential observability. So differential observability is taking a look at the application from multiple different viewpoints. So for my e-commerce application, I might be monitoring my application servers and my web servers, and there might be no problem from that standpoint, right? I'm processing requests, the resources on these instances are just fine. But from a user's perspective, that user might be having a bad time. They might have timeouts or unexpected errors. So we need to be monitoring from both those aspects, and as well as other aspects. Maybe a third-party synthetic monitor that we should have to actually look at the workload as well. So next, I'm going to hand it over to Sungjun to talk through some organizational failover strategies.
Thank you very much, Joe, for going through multi-region fundamentals. And hello, everyone. My name is Sang-Jun Kim. I'm a technical account manager supporting enterprise support customers in implementing best practices and optimizing their workload on AWS. When developing a multi-region failover strategy, you need to consider the components and their dependencies, as multiple applications often form a user story which outlines a specific capability offered to an end user. In this segment, we'll explore 4 generalized failover strategies. Let's start with component-level failover strategy, which is the most granular approach. It allows failing over individual application components to a different region when issues arise. For example, if an RDS database in one region faces problems, the application can fail over to using an RDS instance in a secondary region. This decentralized strategy provides flexibility and autonomy to individual applications by allowing components to fail over independently. However, it comes with trade-offs. Since the secondary RDS instance is in a different region, there will be added latency, leading to potentially varying performance behavior. Also, switching components between regions often requires runtime configuration changes, which can be unreliable during a failure event. Another challenge is the complexity of testing. With so many test configurations, it's becoming challenging to test every combination. This is an unreliable strategy, as we don't know which component will fail and how it impacts operations of other workload components. This strategy doesn't provide a 100% guarantee of success. So with these trade-offs, this is not an approach we recommend or advise for customers. Let's move on to the next strategy, the application failover strategy. This approach allows each application to autonomously fail over all of its components together to a secondary region. By keeping components of an application within the same region, it eliminates the latency trade-offs associated with component-level failover, where individual components might be spread across multiple regions. This strategy significantly reduces complexity by limiting each application to just two possible configurations, primary and secondary. However, allowing individual applications to make their own failover decision can introduce the same varying performance behavior we saw with component-level failover, just in a different dimension. In the worst case, 50% of the application in a user story could fail over, while 50% don't, meaning every application interaction could be a cross-region request. Additionally, while less complex than component level, testing every combination across regions remains challenging. And again, it's not the recommended approach. To address the complexity of the previous strategies, you can build dependency graphs so that all interactive components fail over together. By keeping the connected applications that support a specific user story together, this reduces latency, complexity, and avoids the varying performance behavior we saw with other strategies. However, this strategy introduces its own set of challenges. Identifying all dependencies and building and managing these dependency graphs can be complex, especially in large organizations with a large number of applications and user stories. Seemingly unrelated user stories might share dependencies. For example, if two different user stories rely on the same authentication system, failing over one graph might necessitate failing over the other as well. Even with these challenges, we'd recommend this approach over the first two. Finally, let's discuss the portfolio failover strategy, which is another recommended approach. This approach involves failing over all applications in your portfolio simultaneously, regardless of whether they are directly impacted by a failure or interact with affected applications. The key advantage here is the simplicity. This strategy helps remove the operational burden of creating and maintaining dependency graphs for every user story your business supports. However, it requires a major investment to enable every application to operate across multiple regions, unlike strategies focusing only on critical apps. You can make this more targeted by applying it to specific tiers of applications, like failing over tier 1 applications together, as long as there are no dependencies on lower tier applications. Now that we have explored organizational failover strategies, let's address a common and important question. When should you actually initiate a failover? Determining the right time to failover is essential for ensuring business continuity. Let's explore some key considerations and guidelines to help answer this question. A failover decision tree is a pre-planned decision process that guides you on when to initiate a failover. It's not something you want to be figuring out in the heat of the moment when systems are down. By creating this decision tree ahead of time, you ensure that you're making a rational, thought-out decision rather than a reactive one. To develop an effective failover decision tree, keep these key principles in mind. First, your metrics should be clear and unambiguous. You need to define specific, measurable thresholds that trigger a failover decision. These could be related to system performance, error rates, or business impact. For example, you might decide to fail over if your application's error rate exceeds 5% for more than 15 minutes, or if latency increases beyond a certain threshold for a specified period. Second, integrate your decision tree into your overall operational continuity strategies. It should align with your business continuity plans to ensure that your failover decisions support broader organizational goals. Also involve cross-functional stakeholders across technical teams, business leaderships, customer support, and other relevant groups to balance technical considerations with business needs. By creating a clear, well-defined failover decision tree ahead of time, you will be well prepared to make quick, confident decisions when incidents occur. Now, let's discuss a critical aspect of failure decisions that often gets overlooked: the absence of information. In an ideal world, we would always have all the data we need to make informed decisions. But in reality, we often find ourselves in situations where crucial information is missing. Let's explore how to handle these scenarios. First, let's consider what happens if the designated decision maker is not available. It's crucial to have a clear chain of command and delegation of authority established in advance. Your failover plan should specify who has the authority to make these decisions and who their backups are. Next, we might face a situation where we have incomplete or missing metrics. Your systems might be partially down, or your monitoring tools might be affected by the same issue impacting your main services. In these cases, it's important to have predefined thresholds for partial information. For example, if you can get data from 30% of your system, that itself might be a trigger for failover. Another common scenario is when there's an AWS service event in progress. You might not always have a clear ETA for recovery. In these situations, it's important to work backward from your bounded recovery time, which is the maximum downtime your business can tolerate, defined as part of your business continuity planning. For example, if your business can tolerate up to 2 hours of downtime, and failing over takes 30 minutes, but you've already been down for an hour without an ETA, you'd need to initiate a failover to meet your objectives, working backward from your 2-hour bounded recovery objective. The key takeaway here is that a lack of information shouldn't paralyze your decision-making process. By planning for these scenarios in advance, you can make confident decisions even with incomplete data. Now, let's focus on recovery best practices. First, let's talk about the steps to declare a disaster. Your failover runbook should clearly outline the situation, action, and owner for each potential disaster scenario. This ensures that when an incident occurs, there's no confusion about who has the authority to declare a disaster and initiate the failover process. Your runbook should include a detailed procedure for how each team member should respond once a disaster is declared. Next, specify communication protocols for how employees will establish contact and share information throughout a disaster, including phones, alerts, media, and other communication methods. Your runbook should be detailed enough that anyone with the right access could follow them, even if they weren't involved in creating the plan. This eliminates the reliance on tribal knowledge and ensures that your disaster recovery process is repeatable and consistent. Each step in the runbook should specify what scripts to run, how to run them, the expected outcome before moving to the next step, and who is responsible for each action. Lastly, during a failover, you will likely need access to various systems and services, possibly with elevated permissions. Ensure that the necessary credentials are available in both your primary and secondary regions. It's also a good practice to regularly review and update these credentials as part of your testing and planning. Let's walk through an example of how a recovery timeline might look in action. We'll use a hypothetical scenario involving an online shoe store to illustrate the process from detection to full recovery. Imagine our shoe store suddenly experiences issues. At 5 minutes, we start seeing the first signs of trouble. There's an increase in latency, and we notice a significant drop in incoming orders. Notification systems immediately send alerts via email, Slack, and pagers. For the next 25 minutes, first responders attempt to resolve the issue. However, in this case, they were unable to quickly fix the problem. At 30 minutes, leadership is engaged for escalation, bringing in additional resources and decision-making power. 5 minutes later, at 35 minutes, based on inputs and predefined runbook criteria, a leader declares initiating the failover process. Failover begins at 40 minutes using an automated dependency graph failover strategy to move interconnected systems in the correct order. Finally, at 55-minute mark, our failover is complete. We are now operating in a new state with our systems running in the secondary region. So from the first detection of the problem to full recovery, our total recovery time is 55 minutes. Let's take a moment to review key checkpoints for a successful multi-region journey. First and foremost, remember that AWS infrastructure is designed to meet your multi-region needs. However, to be truly successful, you must remember the fundamentals we discussed earlier. One critical aspect is deciding when to fail over before an instance occurs. Having clear predefined criteria for initiating a failover plan can save precious time and ensure rational decision-making during a disaster. Next, it's essential to choose a failover strategy that aligns with your business needs, technical capabilities, and organizational structure. Lastly, and most importantly, test, test, test. A failover plan is only as good as its execution. Conduct regular, thorough testing simulating real-world scenarios with all relevant teams. So with that, I'm going to pass it over to Jamin to talk about Samsung Account's multi-region journey. Thank you.
Thank you, Sang-jun. My name is Jamin Kim, and I'm DevOps lead for Samsung Account. In this session, I will give an introduction about what Samsung Account is and why we had to fail over quickly, even in case of region-level impairment. And then I will share our global disaster recovery architecture based on multiple regions. Based on over 1.8 billion user accounts, Samsung Account is an account service that connects more than 60 services and apps in 256 countries. It's not just used for major Samsung electronics services like SmartThings, Samsung Health, and Samsung Pay, but also utilized as an account service across various devices, including mobile, wearable, TVs, and PCs. Moreover, it provides a secure and stable customer experience with one account across different customer touchpoints, such as online stores like Samsung.com, offline stores, and customer services. As we say, do everything Samsung with one account. Samsung Account is a core service that brings together 1.8 billion users into a Samsung ecosystem. Samsung Account is a business critical system that connects all Samsung devices and over 60 services, handling a significant amount of traffic while striving for a high level of RTO. Given its global operations spanning 3 regions, it requires an architecture capable of overcoming regional failures beyond backup and recovery within region or age-level disaster recovery. Hence, we implemented a global disaster recovery architecture. Samsung Account is a global service designed to support login services based on 3 AWS regions in EU, US, and AP. Currently, Samsung account stably handles larger amounts of traffic, reaching 2.7 million per second from devices, web, and associated servers. To minimize operational complexity as a system handling this huge volume of traffic, we improve our architecture by adopting a microservice architecture, which consists of over 70 microservices. All these microservices are operated based on Amazon EKS for high availability. We use AurorDB as our primary databases, which process 200,000 transactions per second. Each of the three regions has its own database cluster, which is synchronized through our self-developed solution. We are also improving the architecture using a synchronization system based on MSK. In addition to AurorDB, DynamoDB, and Elastic Cache are being used for data and cache support. For performance improvement of web-based services such as Samsung.com and QR login, we provide them based on CDN. Recently, we migrate the CDN to CloudFront. To ensure high level of disaster recovery that can withstand even regional impairments, Samsung account need to make some key architectural improvements and address existing issues. First, we deploy the service to a new AP region to complement the existing EU and US regions. However, since both regions were already handling a substantial amount of traffic and approaching the limits of their cloud infrastructure resources, a regional impairment could have resulted in complete service outage. To mitigate this risk and distribute a traffic load, we successfully constructed a new AP region last year. Second, there was an inconsistency in service configurations across different regions due to the distribution of over 70 microservices. This means that if a particular microservice was present only in the EU region, the US region couldn't independently support its functionality. To solve this, during the build-out of the AP region, we combined the sets of microservices distributed across each pair of regions and extended them to the remaining two regions. Consequently, now, every single region can cover 100% of all services and functionalities. Lastly, as a global authentication service operating in over 256 countries, Samsung account has established and maintains a mandatory data synchronization architecture among the three regions. Data synchronization primarily involves two databases, AurorDB and DynamoDB. For AurorDB, synchronization is performed using self-developed synchronization pipeline with a CDC and MSK-based synchronization architecture. With respect to Amazon DynamoDB, synchronization is achieved utilizing DynamoDB's native synchronization solution known as a global table. By establishing the new AP region, ensuring consistent service configuration across all regions, and implementing data synchronization, each region has been transformed into an active-active architecture, allowing them to independently execute a single service. Therefore, even if a specific region experiences a problem, the other two regions can promptly observe the traffic. With the upgrade on global active-active architecture, consideration needs to be given to routing traffic to another region. Given the large amount of traffic handled by Samsung account, it was essential to consider implementing the most efficient traffic routing control method at minimal cost. For managing traffic routing upon failure, we examined two main scenarios. The first scenario involves a global load balancer-based traffic routing control method. A global load balancer independent of individual region is deployed, permitting web and API traffic to be rerouted to another region in the event of regional impairments. AWS Global Accelerator can act as a global load balancer, providing the benefit of instant traffic routing, allowing for extremely short RTO target levels. However, for Samsung account, which handles a huge amount of traffic, the notable drawback of a high cost. We devised a DNS-based traffic routing control method. This approach utilizes Amazon Route 53 to modify DNS records to another region in the event of regional impairments, thus altering the client access IP without requiring a global load balancer. This method presents the advantage of zero operational cost, as no additional infrastructure such as a global load balancer is required. And it simplifies failure response task by merely modifying DNS records. Considering expense and reducing operational complexity during failure recovery, the global disaster recovery architecture of Samsung account selects the DNS-based traffic routing control method. We set up multi-region architecture to perform traffic routing control based on DNS and confirm that it takes more than 10 minutes for actual large-scale traffic routing. Samsung account identified the part caused by ISP's DNS cache between real user and servers. In addition, as a global service, Samsung account is provided based on 3 regions, but there was a high latency for users far from the service region. To address these 2 issues, we decided to expand the use of CloudFront, which had been applied only to our web service, to all API. By leveraging CloudFront's AWS Edge network, we were able to achieve mass traffic switching within just 3 minutes. Because actual DNS switching took place within AWS itself. Moreover, through over 600 POPs distributed worldwide, we reduced the average delay time in API transmission by approximately 70%. During discussions about DNS-based failover traffic control method with AWS, we encounter critical issues. AWS Route 53, responsible for DNS record setup and modification, has its control plane built on the infrastructure in the US East 1 region. Therefore, if a Route 53 control plane issue occurs in this region, changing Route 53 DNS record becomes impossible. To address these concerns and improve availability, AWS launched an application recovery controller. Despite any potential failure in Route 53 control plane, ARC enabled pre-configured sets of routing control in the data plane to switch traffic via health check functionality. Let me illustrate how disaster recovery is executed when the Route 53 control plane encounters a problem based on ARC. In case of normal state, the primary routing set configured in the data plane guides incoming traffic to the US East 1 region. Upon detecting a failure during service monitoring, a traffic routing control request is issued using ARC Check API. After receiving the traffic routing control request, the standby routing set previously configured in the data plane begins routing incoming traffic to the EU region, guaranteeing traffic diversion regardless of the circumstance. Consequently, by leveraging ARC high availability features, Samsung account has ensured robust regional disaster recovery architecture. Given that Samsung account is a large-scale service handling a significant amount of traffic, it requires over-provisioning, meaning increasing the size of service and infrastructure beforehand to proceed failed traffic in another region. Furthermore, when setting up a new region, we augmented its capacity to reliably accommodate failed traffic. Nonetheless, there emerged a need for predictable traffic distribution architecture that allows us to directly manage the quantity of failed traffic dispersed to each region and optimize expense related to over-provisioning. We evaluate 2 types of traffic control method provided by Route 53, latency-based routing, which distributed traffic to region with the lowest delay, and geolocation routing, where DNS queries are directed based on their originating locations. Although latency-based routing guarantees optimal speed, it doesn't enable us to define the service scale because the rules for routing are managed by Route 53 instead of service itself. On the contrary, geolocation-based routing permits us to establish national rules and exert direct control over them. By utilizing Route 53's geolocation-based routing scheme, we could achieve overall traffic on countrywide basis and plan for distributing and observing failed traffic accordingly. Implementing the geolocation-based routing method presents a new concern. Route 53 geolocation-based routing supports specifying approximately 256 countries separately for recording settings. Although this offers benefits such as predicting traffic for each country, but it substantially increases operational complexity. So we need to start exploring ways to group countries. Samsung account identify a solution involving CloudFront edge locations. To provide a brief overview, CloudFront is a web service that quickly delivers static and dynamic web contents to users. Leveraging a global network of data centers known as CloudFront edge locations, currently there are 10 CloudFront edge locations situated across the countries. And users access Samsung account service through the geographical nearest CloudFront edge locations. By grouping the three regions into respective CloudFront edge location countries, it is possible to divert traffic to another region following predetermined failover traffic distribution plan in case of failure in particular regions. For example, suppose the US region initially handled Korea, Brazil, and US CloudFront edge location traffic. Then, in case of problem in US region, Korean traffic can be diverted to EU region, while Brazil and US traffic can be distributed to AP region. By combining Route 53 ARC, geographical routing, and CloudFront edge location accessibility, we finally create a geo-latency routing architecture that guarantees high availability and facilitates disaster recovery operations. Let me summarize the entire global DR architecture using account.samsung.com as an example. When a user accesses the service through account.samsung.com, they will reach one of the CloudFront edge locations in a certain country. Suppose the user reaches the edge location in Brazil, they will be routed to the internal DNS URL br-account.samsung.com, which corresponds to Brazil among the 10 edge locations. Next, they will be directed to Failover-br-account.samsung.com, which has Route 53 ARC-based disaster recovery routing enabled. When normal conditions, the traffic will ultimately be routed to the domain in the US region that handles Brazil traffic for final processing. However, if a failure occurs in the US region and disaster recovery mode is activated, Brazil traffic will instead be rerouted to the domain in AP region for handling failed traffic. One more aspect we consider was a rare possibility of a CloudFront edge location expansion or non-edge location traverse traffic. To handle any potential traffic generated by those scenarios, we applied Route 53 latency-based routing to default value of geographical routing and register domain for 3 regions. We configure ARC to exclude the domain of the affected region in case of failure in specific region. The static contents of a Samsung account web are served based on S3 buckets. As S3 is a regional resource, although dynamic contents can be addressed through the geo-latency routing architecture in case of failure in specific region. Static contents remain unprotected against such an incident. To solve this issue, we store the web static contents redundantly in both the primary and secondary region in S3 and group them using CloudFront origin groups. This way, even if a failure occurs in the primary region, the static contents stored in the S3 of the secondary region can be used for service provisioning. Samsung account decided to validate a global disaster recovery architecture it had established in real-world production environments, actively handling massive amounts of traffic. Although conducting validation in live operation conditions entailed considerable risk, including the possible of encountering failures, through planning allow us to proceed confidently. Our verification process involves functional testing to verify the proper functioning of the global disaster recovery architecture, and stress testing to assess its resilience against heavy traffic loss during disaster recovery. These tests were conducted in line with the standard development validation procedures. Functional testing was carried out shifting 2% of total traffic through the global disaster recovery system. Geo-latency routing generates and manages a large number of internal URLs. During this functional testing phase, we were able to identify missing URL configurations early and take correct actions. Load testing was divided into two stages, comprising 10% and 50% of total traffic respectively. Overall system components such as service, EKS, and DB underwent extensive stress testing. Finally, the game day arrived. In accordance with the simulated scenario of the failure in specific region, 100% of traffic from one region was successfully switched within minutes. To enhance observability, Samsung account defined two main categories of faults and established a comprehensive monitoring system. The first category includes errors arising from the service and infrastructure, such as API error rates, sudden drops in traffic, and infrastructure failure events involve EKS database and caches. Additionally, functional errors possibly triggered by new feature developments can be identified through APM. The second category encompassed end-to-end monitoring, which detect errors occurring in actual user environment. Synthetic tests were implemented to test the core functionalities of the service, including login, find ID, password resets, and authentications. Across various countries and environments, real user monitoring, RUM, metrics were also established based on frustration signals and error occurrence rates in specific countries, facilitating swift and accurate detection of issues exclusive to the user environment, such as network disruption. Samsung account has a three-tier operational structure. Tier 1 monitors systems all day, receive alerts from monitoring dashboards, and escalate incident to Tier 2 upon detection. Tier 2 conduct initial root cause analysis and may seek assistance from Tier 3 for further investigations and resolution decisions in case of persistent or severe issues. In the past, when failure occurred, approval from Tier 3 before initiating remediation measures often lead to lengthy delay. However, by enhancing observability, we have improved the ability for Tier 2 to make a fast decision-making and to fast failover immediately with a simple failover script without Tier 3. Samsung account has successfully established a global disaster recovery architecture capable of swiftly recovering from regional issues, achieving a reduction in mean time to repair. Furthermore, we have improved our detailed server and infrastructure monitoring systems and implemented an end-to-end monitoring system to instantly detect errors and performance degradation experienced by users. This allows for faster fault detection and decision-making, ultimately enhancing the resilience of the Samsung account service by minimizing mean time to detection. Thank you for coming. Please complete the session survey in the mobile app. Thank you.